Okay, so let us start. So, like I said, originally our scheduling, right? So it's supposed to be Monday in person and Thursday, online. And so I'm not so sure if we have the classroom, right, in class on Thursday, because we figured out how to do the lecture, right? So people can attend either way. So actually, it doesn't matter. Just kind of asking, does it matter to you that we meet in person on Thursday if we can, or actually online is good? If online is good, then I don't have to, worry about, room availability on Thursday. What's your preference? One second here. Right. I mean, sure. But like I said, right? I mean, if we meet in person, you can still attend online because, right, the meeting will still be kind of projected online, right? Okay, so no one needs to meet in person on Thursday, then we'll just keep this then. Any objection, anything? Let me know. Okay, so like I said, right, if you want something, you better say it out loud. Seems to me then we'll just keep the schedule, all right? So Monday in person, Thursday online, all right? That sounds good to me then. All right, so back to where we were last time, right? So last time we started to kind of discussing, right, the Brownian motion Black-Scholes model structure. So from now on, right, I'll just abbreviate Brownian motion by BM because it's just we use that term a lot. So WT, right, is a Brownian motion if, right? The first is just a starting condition that conventionally we always start at 0, but we don't have to, right? We can start at other points if we want to. So the first is not essential. The second and third, right, are essential. W has IID increments. And third, right, the increment has normal, right, distribution with variant, right, scale like time, right? So like that. Okay. So basically, right, B means this, right? If R is less than S less than T, for example, then WT minus WS will be independent of WS minus WR, right? So for non-overlapping interval, then the increment, right, meaning the change, so increment, right, means change, right, are independent, right? So pay attention, right, that this doesn't mean that WT is independent of WS, right? In fact, that's not true. Okay, only the increments are independent. So again, right, the differentiation here is like the stock price versus the returns, right? When you first kind of look at these things, right, I mean, they kind of all look the same, but conceptually they're very different, right? Because in terms of stochastic behavior, right, they behave very differently, right? So it's the increments, okay, that are independent. So again, kind of think about like, increments is like the returns of the stock, and Brownian motion is like the stock price itself, right? They're different objects. I mean, they're related, but they're different. What else? So notation-wise, right, increment will be denoted by D D for differential, derivative, difference, whatever, right? If I want to really spell out the time interval, I might do something like this, right? I don't know. My notation change from time to time. Sometimes we can also do this, right? Delta. Again, right? So I think delta is longer to write than D, so I'll just stick with D. But let me explain. The D is like the notation that's used for continuous, right? Notation when you push to a limit, like the integration. Delta, right, is used for discrete notation, like when you sum, right, over like a Riemann sum. Okay. Now that's when you want to be, rigorous. Like I said, when I'm lazy, I'll just use D for both scenarios, unless there's a real need to differentiate the two. Is that okay? So D or delta, for now, right, both denote the change, right, which is the kind of the increment as well. Any question so far? So then, right, like I said also last time, an important identity, okay, which is like stochastic integration 101, or actually any kind of integration, okay, not even stochastic, is this, that if you integrate, right, the differential over a time interval, you get the big differential. Okay. So notice several things, right? You got to write this right. I know that, again, right, there are a lot of notations to manage, but so what we say, right, is we move from time interval from S to T, right? U here is like a dummy variable, right? That's used to add. So U has no real meaning, but it's super annoying if you write something like this. Okay, because S is not supposed to change. So that has a complete different meaning than, U, you understand? Or T, right? I understand sometimes accidentally, right? We don't pay attention. But, if you can, right, and you should try to pay attention. We're summing, right, the interval from S to T, and U is a moving variable, right? U is a dummy variable. Is that okay? And so, right, this is an identity that the thing though, right, is significant because this is actually already pushing to a limit, meaning that this is a differential, right? But at the heart of it, right, is pretty trivial in the sense that, right, you're just saying something like W, right, T1 minus WT0 plus WT2 minus WT1, etc., plus WTN minus WTN minus 1. This is equal to WTN minus WT0, where, of course, right, what we have in mind from S to T like this, right, and this is T0, and this is Tn, and this is T1, this is Tn minus 1, etc. Is that okay? So this is just a telescoping sum, right? So when you add the changes, you get the big change. Is that okay? So nothing really big, but it's the bread and butter of how we reconstruct, right, a function out of this differential, right? A lot of other things are built on top of this kind of trivial kind of relation. Okay. Any question? So, I mean, if you want another, right, motivation, I think this will be no surprise to anyone, right? That if you add dt, you get t minus s, right? So this is your good old integration, actually. Now, so but right, this actually even generalized like this, right? Like I said, this works for anything. So it's an identity, right? Here, notice that here we didn't even need the fact that W is a Brownian motion, right? This is a telescoping sum, so algebraically. Okay, you know what? Either ask that before the lecture or after lecture, all right? I'll be happy to answer that, but we're in the middle of the lecture, so let's just focus on this. You want to stay after class, or we can discuss that a little bit, all right? So yeah, so back to here, right? We want to what do I want to say here? Yeah, there's nothing about Brownian motion, right, that needs to be used, right, for this to work. So in fact, this holds for any process, all right? For example, here, this is just time itself. This is Brownian motion itself. So it also works for stock. Oh, the notation is a little awkward, right? Because S of S. So let me try to see what I can change here. Maybe R to T, right? So it's just 2 time points, right? So again, what are we saying here, right? If you pick, right, 2 time points over this time interval, you add the change in the stock price, right? So daily stock change in price. Notice it's not returns, right? This is just stock price change. Then you get the big stock price change. Yes. So again, right, I want to say that all these identities are very, very trivial, but they are fundamental to reconstruct things, right? So how are they important? First of all, you will see that we use this all the time in simulation. Okay. For example, how do we simulate a Brownian motion path? Right. So remember, right, the Brownian motion is an object that is in continuous time, right? So of course, when you simulate, you basically just try to sample it through some discrete time points, right? You cannot simulate it continuously through time. You simulate it through discrete time points. But then how do you, right? So basically, for example, let's say you want to simulate, right, Brownian motion from 0 to big T. Yes. Now, of course, you want to have some discrete time points like T0, T1, etc., right? And let's say this is T0, 0, right? So this is T1, T2, right? This is Tn minus 1. Now, then what you want to simulate the Brownian motion on these time points, right? And of course, W0 is 0, so this is fine, right? You initialize this point to 0. Then what do? Well, right, so you see exactly that the increment, right, is what you use. And then the reconstruction, right, of the Brownian motion from the increment is what you use. So what does that mean, right? What that means is, first of all, right, you generate the dW, right, Ti plus 1 as IID normal with mean 0 and variance dt. All right. And then you go through, there are probably faster way to do this, but you can go through, you can recurse, right? You can loop through I, right? And then WTI plus 1 is WTI minus 1 plus DW, TI plus 1. Sorry, not TI minus 1, right? TI. Right. So first you generate the increments, and then you reconstruct the Brownian motion from the increment. All right. Question? So similarly, right? How do we generate a Black-Scholes, right, path? By Black-Scholes path, I mean, right, the stock price. So again, right? Notice that we have here. I hope you don't take this too trivial, right? We do have like the stock price like this, right? ST to be S0 e to the mu minus 1/2 sigma square times T plus sigma WT, right? Let's just say that this is the physical probability. So we take it to be mu instead of R, okay? So even though you have this model, right? The formula, you have to be careful. So first of all, remember that we also have the so-called percentage return, right? Like this. Sorry. Okay. So I asked you to trust me that these two are the same for now, right? I only asked you to use it, and we'll explain why they're the same later on. But even if you trust me that these are the same, right? And you know you have access to this. So how do you generate a Black-Scholes path, right? Using either of these ones. Okay. I hope that that's still something to be thought about. And so here's one way, right? First of all, this is percentage return, right? I write it this way to, again, make sense, right, of the finance that the percentage return, right, has return rate mu and has, kind of the variance rate, right, sigma square. So, but in terms of like reconstructing the stock, right, this will be a better way to express it. Okay. So notice, right, we're playing around with notation, but this actually works, right? So we just multiply ST on both sides. But notice that while this tries to tell us about the return, right, the percentage return, this tells us about the stock price change, right, the change in the stock price itself, right? The problem, of course, right, is the right-hand side now depends on ST as well. So this, right, because the left-hand side and the right-hand side both depends on ST, which we suppose is unknown to us, right? Remember, the point of view is we start from here and we try to go here. So we don't know this, right? We pretend we don't know this. Then this, right, is properly a stochastic differential equation. All right, or SDE. Again, the reason is, right, both the left-hand side and right-hand side, right? So the left-hand side has the differential, right, or the derivative of the thing we're looking for. The right-hand side has that thing as well. So it's an equation, right? And it's stochastic because it's random, and it's differential because of this, okay? But again, right, notice that the SDE itself just comes from the model of the percentage return, all right? Just comes from the model of percentage return. Again, right, learning how to solve this, etc., can take the whole course, right? There is a graduate course on SDE, right? I mean, back when I went to school. Anyway, that's not what we're focusing on here, right? We're focusing on, kind of simulation, the practical aspect of this kind of modeling. So, right, as far as we're concerned, as long as we know how to access the differential, right, then we can do the same thing. In other words, right, you suppose you want to generate a stock price once you do T, yes, then you first of all break it down to time intervals, because that's the only thing you can do, right? Generate the stock price on these time intervals. Then you initialize, right, the initial stock price to S0, like 100 or whatever, right? I mean, that's given. And what do? Then you first of all notice that the differential of the stock is driven, yes, by the differential of the Brown motion. So your starting point, right? So this is like your white noise source or your random source. So you have to start out with this guy again, right? So first you want to generate the Brown motion differential. Okay. And then what do? Then actually you see, right? The differential, right? Let's take it slow, right? the change of the stock price, let's say from T0, T1. Yes. And we'll talk about this later, but let's say that this is S0, right? So it will be mu S0 dt plus sigma S0 dw T0 T1. Okay. Agree so far? Any question? Now, right, but pay attention. Of course, right, we only know the stock price here. We don't know the stock price at any other time points. On the other hand, this formula, right, coming from our model of the percentage return, allows us to compute. Yes, because notice everything here is known, right? This one is generated from our simulation. So everything here is known. So we can compute the differential on this time interval. Okay. So right. So that's a good question, right? Depends on what you mean by correct. So this is an approximation, if that's what you ask. Yes, because I mean, well, we are doing discrete time points anyway, right? So the question of correct here is a bit of a, not a precise question, right? You can ask, is it a good approximation of something? And yes, right? Because again, think about it, right? What are we saying here? Even in the percentage, right? You think about it, right? What is the meaning in the percentage return? The percentage return, right, over this time interval will be something like ST1 minus ST0 over ST0, right, is mu dt plus sigma, right, which is here what we mean by. Yes. So it's indeed, right, S0. Does that answer your question? Yeah. I mean, actually, your question is actually deeper than that. There is a very subtle point in stochastic integration. Sure, whether you use the left point or use the right point. In other words, you could use S1 here, ST1. And funnily enough, normally you would think it doesn't matter. Here it does. What point you use will result in a different kind of stochastic integration. What we use here is called Ito integration, which perfectly corresponds to our finance integration. But if you use the right point, like ST1, then you will end up on something called, wait, hold on. I don't know about right point. There's a midpoint. If you use a midpoint, which is somewhere here, then you will end up on something called the Stratonovich integral, which is used in engineering. And I think the right point has another. Anyway, right? The whole point is, and we haven't got to that yet, that stochastic integration is complex, right? It is highly dependent on what point you use. So yes, your question is relevant. That's kind of a little bit too far, like out there that for now, right, I want to kind of just stay with the finance and kind of, right, say that yes, financially we are really following what we're doing, right? Because that's how we compute percentage return. All right. Okay. So what this means next is then ST1, right, can be computed. Because, right, ST1 then is just ST0, which is S0, right, plus the change. All right. But then, right, now once you can move here, then you can just repeat and move like that. And then again, right, what am I using here? I'm using exactly this idea. Any question? So, right, what I was demonstrating to you that is, right, even though these equations are trivial mathematically, I guess, right, they are used very, very heavily, right, in simulation. And in fact, right, simulation relies on that idea mostly for now, right, for the path. Okay, so let's see here. So for example, right, let's show you. So this is like the binomial, right, approximation that I was talking about last time. But now my focus is not on the binomial approximation. My focus, right, is on how I generate the Brownian motion path, right? So here, right, see, look at the code. Sorry, this is the stock path. Hold on. Oh, no, let me see. Sorry, this is a stock path. Let me go here. Give me one moment. I'm looking for what I want to tell you, and somehow I'm a little bit lost. One of these, because I kind of use different oh, I did not use the all right. So I did not generate the path like that. Maybe I'll give you a homework to do that to see this. So sorry. So in fact, let's take a look at this, right? So here, let me see. For the Brownian motion path, right? You see, I did do that, right? I generate the dW, right, which is the Brownian motion increments, right? Or I call it Brownian motion differentials. Okay. Let me make sure am I still sharing the right screen?
I think you won.
Okay, cool, thanks. Yeah, just make sure you understand what I'm talking about, right? So I did generate the Brownian motion differentials, right? And then what am I doing, right? By adding the differentials, what am I doing here? I reconstruct the Brownian motion itself, right? I reconstruct the Brownian motion itself. Except here, right, that I cheat, if you will. I did not use the stock price differential to reconstruct the stock. What did I do? I just used the direct formula, right, for the stock, which is S0 time, right? The mu minus 1/2 sigma. So I used the explicit formula to reconstruct the stock price itself. I did not use the differential formulation, right? If I were to use the differential formulation, what do I do? I would do something like, right? So I did say that here is stock price using the explicit formula. If I were to reconstruct the stock using the differential, I would do something like this, right? I would have to do ds, right? I have to do ds, which is something like numpy zeros, right, to begin with. Let's say size n, I believe, right? And then here, right, I would do something like ds, right? I would be s, right? I think somehow I call this s1, so whatever, right? Let's call it s. Something like ds will be s I minus 1, so si, sorry, right? Something like that times, right? Mu times dt, right? Plus si times sigma, right, times dwi, all right? And then I would do something like si equal to si minus 1 plus dsi, something like that, right? Maybe my I minus 1 is off. But basically, right, this will be constructing using, right, differential, SD. You understand? And the point is, right, that if our stochastic calculus is correct, then the way I generate, right? So maybe I should call this S1, who knows, right? Basically, the way I generate, right? The two different ways that I generate the stock price, right? Using the explicit formula and using the differentials will be the same, meaning I get the same path. All right, if my stochastic calculus is correct. You understand? So, right, once we verify that, then it doesn't matter which one we use, right? You can use the differential approach or you can use the explicit formula approach, right? But notice with the Brownian motion, you cannot directly simulate the Brownian motion. You have to do it using the differentials, right? But with the stock price, because we know how the stock price is directly related with the Brownian motion, we can either use either one. So I'll assign this as a homework, right, for you guys to verify that these two ways to generate the Brownian motions give you the same stock price path. Sorry, not generate Brownian motion, generate the Black-Scholes model, right? You understand the difference or the point of kind of what I'm trying to say here? Right, and in fact, right, verifying that these guys are equal, right, exactly is verifying that the stochastic calculus works in the same way. Okay. All right, so that's that. So I guess to demonstrate, right, see if you are, these things are delicate, right? To demonstrate if these are correct, to see if you understand this is correct or not, right? So here's a question, is the following correct? So I want to generate a Brownian motion, right? Then let me say that I will generate, right, independent, right, normal, 0, t, let's say ti, right, and assign w, right, ti to be normal, 0 ti. So actually, right, what do I mean by this? It's quite simple, right? So basically, you have the time interval 0 to t, right? And then you discretize it. And then so actually, what you do is you kind of generate independent normal, right? Independent standard normal, which is kind of standard. Right, 0 to 1. And then from these standard normals, right, you let WTI to be square root of TI times, right, normal 0, 1. Does that make sense? Then you get WTI to be normal 0 TI. So if I want to generate a Brownian motion path, is this correct? This is much faster, right? Why go through the loop and add that kind of thing, right? Notice the way I was saying was you generate dWt, right, as normal 0 dt, and then you loop through the I and then add them and store it, right, in an array. Right here, you just ask numpy, right? So basically here, you just call something like, right, n to be np, right, dot random, dot normal, right? Like 0, 1, and n, something like that. And then for each of the WTI, right? You say square root of ti times, right, n of I, something like that, right? Understand? So it is correct. Maybe there's a silent there. You don't know. You don't care. You don't understand what's going on. Okay. So the question, right, has to do with, so maybe let me go to the code. All right. So here, right, maybe let me copy this, right? So I guess we don't need all these. Right, I just focus on the Brine motion, right? So this is how I generate Brine motion. Yes. And let's see if NumPy is on. Okay, so something like that, right? Looks good. Now what I'm saying, right, is instead of looping through this, can I do this? So basically, right, I would generate something like, first of all, right, let me do 0, 1, n, right? So basically, I just generate ID standard normal. Then I would loop through this and then make sure the variant works. Wi, right, is np dot square root of I over n. Or you know what? Let me just say this is standard normal or something. And of course, right, if you really want, right, so I can even make this, right, ti I over n, right? Oh, I think it's I over n times t, but t is 1. Yeah, so it's I over n. Does that make sense? I'm asking, are this equivalent way of generating Brine motion? Does it make better sense now? What my question is? Or still no? Which one looks like Brine motion to you? I hope. Okay, but what is this reasonable? So right, again, right, in the picture, that's why I wanted to show you, right? But is this reasonable in code? What's wrong with it? What about a partition? So, right, what kind of name do we give this? So, I mean, here too, right? Yeah, this is white noise. I mean, here too, I am also fixing Ti to be I over n, right? It's the same thing. Right, because here, dw, right, here is dt, so it's also I over n. I'm also fixing that. That's not the issue. All right. So the issue is, right, exactly is what I was referring to as about the joint distribution and the marginal distribution. Okay. So here, marginally, both figures, right, generate normal with mean 0 and variance ti. Both of them does that. The difference, though, is the joint. Remember, I keep telling you that Brownian motion, right, WTI is not independent of another WTS, right? WS and WT are not independent. So the fact that you go through and you have a bunch of independent values here, then you just scale it. Of course, this is white noise. So when you scale it, you get white noise back. Understand? Or the difference here is like a random walk versus white noise, which is the step of random walk. So you have to go through the steps and regenerate, right? You have to add back the step to get to reconstruct the Brownian motion. You cannot construct the Brownian motion directly, because when you do this, you will miss the correlation structure or the joint distribution of the Brownian motion. All you can capture is the marginal. Understand or no? Well, the rest of the students. All right, I guess only 2. That's fine. Okay, so this is why stochastic calculus is important. That is, I mean, why is too much, but right, if you understand stochastic calculus, you will see why you have to do things in a certain way and another way, right? Imagine that you are in a big application, right? And you need to somehow do a path because you need to look at, yeah, sure. You need to do a path, right? To do a exotic option. And let's say you are, not careful and you code up the Brownian motion like this. And of course, right, in a big application, you don't have time to plot the graph, right? I mean, why would you want to look at a graph? You just want to calculate, right, in a big pile of code. And your code, right, your price will be meaningless, right? Your price will be nonsense. And you don't know why your price doesn't work, right? Because you generate something wrong. That's meaningless down, okay? So I'm saying, right, the benefit of, like, again, like exploration of concept in the classroom is you can see things with your eyes, right? But what I'm trying to say is, like, conceptually, right? An error like this, I do believe, right? I've seen error like this made before, right? That, if you don't quite understand what Brownian motion is, you can generate something like this. And then you will commit a huge error down the road. If you do something like exotic option, where the path matters. Oops. Okay. So that's wrong, right? So on the other hand, right? How can I just generate? Let's say I want to generate stock, right? I'm not sure if this question makes sense. Again, maybe I'm making a big deal out of something, but basically, before, right, when I say with the Brownian motion, you cannot generate the value directly, but you have to go through, right, the sum. So how can I be confident that I can just generate the stock price directly without going through a sum. Does the question make sense? What's the difference? What allows me to do this here for the stock, but not for the prime motion? Any answer? It's joint actually. The joint will also work. The joint will also work. Well, the reason actually is very simple. Because I have generated WTI correctly. And Ito calculus works. All right. So two things. First of all, that the brine motion, right, has to be generated correctly, meaning you cannot do something like this and then feed in here. If you do something like this and feed in here, of course your stock price is going to be nonsense. I mean, in terms of the path behavior. But if you generate it correctly, like this, all right, then as long as you generate it correctly, then if you do it like this, it's fine. The stock price will get the correct correlation behavior, the joint behavior. All right. But of course, there's another thing that's behind the scene is because Ito calculus works, which, right, again, that's a point that we're going to discuss in the future, right? But the point is that this and this, right, are equivalent, meaning they all give you the same stock, right? And like I said, you can already, right, try to verify this using code at this level, right? The math we'll explain later. But that's Ito calculus, why this can work. But right, the point is, as long as so the driving source, right, of the stock, the noise source is a brine motion. If you generate the brine motion with the correct behavior, then the stock, as long as your formula is correct, your math is correct, it will also inherit the right structure, the right joint behavior. Okay, so it doesn't matter if you use the differential approach or the direct approach for the stock. If you know the direct formula, you can also use it. Question on this? So for the stock, you have options, right? As long as you generate the brine motion correctly. Okay. Now, the third point is this, right? Suppose I want to calculate, let's say just call option price, right? Okay. So you already saw, right, that I want to do the simulation, right? I simulate, right? So the idea is I simulate, like, I don't know, 10,000, right? Values of ST, right? And then take the average. Okay, so again, let me show you that piece of code, which is where? Right here, right? So I want to calculate the call option price. So I just simulate, you see, here I do it a lot. like 10 million or something, right? Values, right, of the stock, and then just average it, right? Take the average. Okay. Now, then here's a question. Here, I just generate the Brand motion, right? WT, which is, where is it? WT is just independent normal, right? So the point is, in this simulation, I did not generate any path. Understand? In this simulation, I did not generate any path. You see it? I just generate Brand motion at right T. You see? Normal 0T. And then I average it. And then compare with the Black-Scholes price, right? How did I get away with that? Do I need to generate the path of the Brand motion up to this point and then plug to ST and then average? How did I get away with this without using the path? Understand my question? Again, right, these are important questions. These are important practical questions. How you simulate something and still achieve the right result. Right, I keep yapping on about, right, path, that kind of thing. So here, right, why didn't I use the path? What is path dependent?
Is it because you're only interested in like the stock price at the last like time period, not the whole path?
Excellent. That's the whole point, right? Yeah, exactly. I think both Fatima and Karim, right? Got it. Yeah, right. Because this is the whole point of European option, right? European option only depends on the value, right, of the stock price at the last moment. So in that sense, I only need marginally the distribution of the stock price at the last point. So generate the whole path will get me the same result. Is pointless or is extra work for no reason, right? In other words, right, the whole point of the European option is it's marginally only dependent on the behavior of the stock price at the last time. So no, right? I mean, if I could generate a whole path, but that's extra work and no one will reward me for anything. So yes, right, that's important. So that's about efficiency, right? If you want to only do at certain time points, that time point only, then you don't need the joint, right, behavior. So only, right, the path I was talking about is means to capture the whole behavior, the whole history. So that's, more properly for exotic option or for American option, right? But for European option or for anything that's only on one time point, then you better off just directly go there if you know the marginal distribution, right? For efficiency. Does that make sense? So that's the point I want to make. All right, so right, I don't only no need to, right? So I want to say here, no need to generate the path, right? That will be really inefficient, right? Because the option. Okay, cool. So again, right, all these things are practical, right, implication of, right, the whole path, stochastic nature of things. So I want to tell you, right, these aspects before we jump into the math. Questions? All right. So now let's go back to the math, right? So let's do some calculation. All right, so this is math proper, things that you will probably do on the exam. So first, for S less than T, let's say what is the conditional expectation of WT on WS? What do you think it is? And how do you show this? I can't, right? I can't answer that question in general. And actually, you know what? It seems like the answer is in the question, meaning, right, what is European option? European option or Euro style option, right, is the option that only depends on one time point. Then, right, again, it's just the idea, right? Because the option only depends on one time point. That's why you only marginally need that value. But then the option, if somehow it stipulate, right, the two values at two time points, then already, right, either you generate the path between those 2 points to capture the right behavior, or you need to know how to compute the joint distribution of these 2 points. So you can only generate them separately, independently, generate these two only, right? So that question depends on how you understand the option and how you understand the behavior of the stock, right? But right, I mean, really, we have to look at what the option says. Yes. So yeah, but Euro, right, by definition, and anything else is non-Euro, I guess, by definition, it means it depends on more than one time point. Then I don't want to say you have to generate the whole path, but you have to generate the correct behavior of those points together. I don't see any easy way unless you want to do the math to capture the correlation structure of those points, or you can just generate the path, right, and capture the point itself. You know what I'm trying to say? So. Yeah. Okay. Anyone has an answer for this? So let's see, right? You will see a lot of calculations like this, okay? In at least stochastic calculus. And the key idea is to use the independent increment. You just want to utilize it a lot. What does that mean? Right? You want to calculate something like this, right? Now, first of all, right, these guys should have some relation that is not quite easy to spell out. But the idea is always that the future can be written as the past plus the change, right, from past to future, or the increment. All right. Now, W, right? Right. WS is known, right, because we're conditioning on it. So we can take it out as a constant. And then we have this. Okay, so far? But now, right, this increment is independent, right, of any past history. So Professor Larson, right, in the notation of 621, properly speaking, will have something like this. Okay, so you know what this means, right? This is the filtration, or actually, we have this, right? This is the filtration of the Brownian motion, right, up to time s, meaning this is independent of any Brownian motion before time s, including s itself. All right. Does it look familiar? Am I saying something that you have seen before? You should, right? What that means is you can drop this by independence. Now, what is this expectation? Zero, right? Because we know that WT minus WS is normal. So therefore, the answer is WS. Okay. Now, in fact, right, I just do this because I want to make it look, simple. But the calculation above, right? Correct. I was about to ask that, but you got it, right? In fact, right, the above calculation can be repeated, right, with this, with no change, right? Because of this. So therefore, is martingale. Okay. So, right, the independent increments is actually can be generalized to this. But I hope it's fine, right? It's not that big of a deal. Any question? All right. So let's do another calculation. What about this? How do we approach this question? So actually, it's the same idea, right? You still split the future as the past plus the change. Why? Because again, you want to utilize the independent structure. Okay. So now, knowing that, right, you will want to expand the square, but keeping this as one single block. In other words, I'm doing something wrong, right? WT minus WS square, sorry. Okay, so far? So I'm conditioning on WS, right? So I know that WS is a constant, so that can go out. And then this, right? WS is a constant, so it can go out because I'm conditioning on it. Then finally, I have this. Okay. So again, right, I guess on this thing, I assume that S is less than T, right? Because past, future. So what is this term right here? Yes. What is this term right here? That's correct. So that's the answer. Okay. Any question? All right. Can you spot a martingale from this calculation? Can you spot a martingale from this calculation? All right, it's a sub-martingale, but can you spot a martingale out of this calculation? It's a sub-martingale because this is positive, right? So it's really W. So this is indeed what do you want to say it, right? It should be bigger than WS, right? So yeah, it's a sub-martingale. That's correct. Am I right? Yeah, right. But because S is bigger than T, right? So, but I'm asking if you can see a martingale out of this. You're right. It's a sub-martingale because of this, right? I mean, T minus S is positive. But what can you? Is there? No, of course that's trivial. But I'm asking, do you see a martingale out of this? You haven't seen some kind of trick to do these things around? So yes, WT squared is a sub-martingale, I agree. Right, no problem. But don't you see that then it also says that WT squared minus T is a martingale? Right? I mean, you subtract T over here, and it's WS squared minus S. Right? So I mean, both statements are fine. Yeah. I mean, again, just some observation, nothing earth-shattering. Both are well-known facts. Okay. Questions? All right. So now I want to ask in general, what's the covariance of prime motion? What's the covariance structure of the prime motion? Okay. Because I keep saying, right, these guys are correlated, but let's see, right? How do we calculate this? So what is the covariance? So covariance, right, is expectation of the product, right? Minus the product of the expectation. Right? These guys are 0, right? So we only need to calculate this. Okay, so actually, so it's just this term. So how do we calculate this? Same meaning. Right, correct, right? So exactly. So, but here, right, we don't know what is past and what's future, right? So maybe we should just make an assumption, right? Let's say S less than T again, right? Because here, actually, when people do this, they may or may not mean S less than T, right? Let us make that extra assumption, which is fine. And so yes, right, you got WS plus WT minus WS, right? So you understand the reason is this, right? It's very subtle, right? Because we'll carry out this calculation. Okay, let's do it now, right? So this is the expectation WS squared, right? Plus WT minus WS, right? Times WS. And that's going to be expectation of WS squared, right? And then we know that these two guys are independent, right? So we do this. And I hope right by now it's not surprising that the answer is S, right? Because this is 0. Right? So I just want to ask this, right? If S bigger than T, are these calculations valid? If S is bigger than T, are these calculations valid? So maybe it's a little bit awkward, right, to look at that. So maybe let's do it again, right? I don't know. So how do I say this? Yeah, I think it's fine. Let's just keep it like this. How do I want to tell you? I just want to tell you one thing. Yeah. So instead of doing S bigger than T, right, I can switch the role of S and T, right? So in other words, the question I have is this, right? WT minus WS and WS, right? So if I switch role, right, of S and T, right, still keeping S and T less than T, all right? So just to make it easy for us to think, but that kind of is the same as saying S bigger than T, right? So is it true that WS, WS minus WT, right? Or that doesn't matter. Is independent of WT if S is less than T. Or if you want, right, we can do WT minus WS, doesn't matter. So the question is, if S is less than T, is WT minus WS independent of WT? Right, the answer is no. Okay, so be very careful. That is kind of interesting, and I'm not sure subtle or not, but right, here's S, here's T, right? And here's the increments, right? So we're saying that knowing the value here does not help you to know how the ground motion will move from here to here in terms of the net change. On the other hand, knowing the value here, there is something you can say about the movement from here to here. All right. So the movement is dependent on the last value, but not dependent on the previous value. All right. So past and future are independent given the past, not given the future. Understand? So in other words, right, the assumption of S is less than T here are super, super important. In other words, right, if S is bigger than T, what should the answer here be? The answer should be T, because now T is the past, right? S is the future. All right. So in other words, right, what's the general answer for the covariance of WTWS? It's going to be the minimum of S and T. The past time, not the future time. That's fine. Don't worry. It's easy to lose track. It's a past time. All right. So yeah, this is the well-known, right, covariance structure of the ground motion. In fact, right, it's true even when S equal to T, right? Because then that's just T. All right. But it's super important to keep this in mind, right? That this is not true. Okay. In fact, I feel it's kind of fun to ask you to compute this. I wonder how hard it is. For S less than T. All right. So I'll think about it. Let's see if you can. Let's see if I think it's not that bad. I'll think about whether I want to assign this as a homework or not. Right. But the point is, you should see that this should not be 0, right? Because they're not independent. This is 0. Okay. Question so far? Oh, actually, it's very easy. It's very easy. I'll assign this as a homework. I know the answer now, but yeah, I won't. I'll keep it a secret. I'll let you think about it. Yeah. All right. Any question? All right. What else? What else? Maybe let's do one last calculation. It's very easy, but this will also be very, very common for us to do, right? Because it has to do with a stock model, right? So what is this? And why is this true? You spilled a secret already for teammate. You let the students do that. You're right. Yep, you're right. Let the students answer that. What is this? In fact, right, maybe what is this in general? Right, it will be moment change function, right? And this will be in general. Yeah, before the sigma, right? Now that I throw in a sigma, then it will be this, right? Yeah. So this comes from, right, expectation of e to the t, right? Normal mu sigma square is e to the t mu plus 1/2 t square sigma square. Yeah, sigma square, all right? But that's fine, right? So this is very, very important for us, right? Because our stock model, right, exactly is S0 e to the mu minus 1/2 sigma square t, right? This is a constant term, sigma wt, right? Something like this, or sometimes we change to r, right? And so we routinely do this kind of calculation expectation of, right, e to minus r, let's say t, right, as t, like this, that, right, relies on this kind of thing. Okay, I think that's a good time to wrap up everything. Any question? All right, so we're done for the lecture. I guess if there's any question about the homework, I'll answer them now.
Thank you.
Yep, thanks. Yes. You mean you're asking if there's any other random source? I mean, of course. Well, we have a jump model where we use, Poisson process to capture the jump of the Brownian motion. But people have done fractional Brownian motion to capture some sort of like, non-independent, kind of some long-term memory, I think. So there's fractional Brownian motion. I mean, closer to home would be something like you try to model the volatility as a stochastic process, right? So as far as I can tell, Brownian motion is a very popular choice to model. It's just easy to use. People have done research work on fractional Brownian motion, but I think the calculation there is sophisticated, right? As far as I know, and so I've seen research paper, but frankly speaking, I'm not super familiar with that. But yeah, I mean, you can try other random sources to capture, certain other kind of dependent structure, right? But I mean, as far as I know, like Brownian motion is still kind of a little bit popular to use, just kind of easy to work with. And then you try to capture the dependence using some other way, like stochastic volatility to calculate. Right. Shinan, right? You have a question about homework?
Yeah, yeah, I have a question.
Go for it.
Yeah, can I explore the question 3 part D?
Mhm.
Yeah, since I run the implied volatility, I have different implied volatility with respect to different strike price from part C.
So what is the question? What's your concern?
Because from part 2, we just calculate one historical volatility, right? Part 2 in question 2.
Okay, let me see here. You're talking about question 3, right?
Yeah, but question 3 just want to compare with question 2's volatility.
Hold on, I am pulling up the question.
Okay.
So let me see here. Question 3, part D, right? How do you compare your answers with historical volatility? Oh, I see.
Yeah.
You know what? I think my point is that they should be different, right?
They should be different. Okay. Yes.
I mean, they should be because I did emphasize that they're just two different objects.
Yes.
Right. Yeah, that's actually, sorry. I mean, I don't mean that to be any sophisticated question. I mean, I want you to realize that these are two different numbers because they have different meanings, right? And that's why we want implied volatility, because if they're always the same, then why go through the work, right? You just use historical volatility. You know what I'm trying to say? So I think the only answer, I suppose, they're different. I mean, there's no real comparison between them, I don't think. It's just different. I mean, I want you to observe that.
Okay, so running the implied volatility, we will have a lot of volatility with respect to different strike price, right? Yeah.
That's true too. There's also that aspect, right? So how to say this? Yeah, so in fact, yeah, I see your question now, in the sense that maybe my question is not very precise, right? Because what do we use to compare? That's true too.
Yeah.
Yeah, I was being vague. You're right. I mean, so here I was just expecting you to observe that the historical volatility and implied volatility are different, you know. But you're right. I mean, what strike do we use? And yeah, I don't know, because of course there's no unique implied volatility like you said. So it's really about people use the concept of volatility surface, right? They use the whole surface as the information. So sure. That's the imprecision on my side. Don't worry about that, right? So basically, you're right. The point is correct.
And I think this will impact the question 4, because question 4 says that we have to take sigma as implied volatility from question 3, and there are a lot of volatility with
So okay, I see what you mean now.
Yeah,
so for question 4, just for one strike. Sorry, just for one strike. Or how to say this, right? You can also use that for the range of strikes that you use in part 3. Because so what I mean, right, is that for each strike you have one implied volatility.
Yes.
But for that, you also have one price, one market price. Yes. So then you can use the implied volatility to plug back into the model to check against the market price for that strike. So for each strike, you have one price to check, and then you can check for all the strikes that you use in part 3. So that one makes sense, actually.
So part 4, we have to check each strike.
Yeah, it shouldn't take long, right? Because you just look through the strikes, or if it takes long, you can check for one strike. I don't care, but I think you can check for all strikes, right? It's better that way. You just look through the strikes, right? Because once you can write a code to check it for one strike, and you just look through the strikes and check it for all the strikes. I think it's better to check for all the strikes, because then you have that idea, right? That exactly like you said, that implied volatility is not a single number for one single strike, right? It's really a range of numbers. So you want to really do it, right? And in fact, people do it for a range of strikes, and a range of expiration days, right? So here I only ask you to do one expiration day, but I think it's better, right? Just conceptually and in terms of practice, you should try to do it for the whole range of strike. It shouldn't make that big of a difference.
Okay.
Does that make sense?
Yes. Can I ask question back to question two?
Yeah, go ahead.
Question two is the annual average rate of the return. This part, the time we use 3 years, like the part A, part B, right? Because this part doesn't mention the year, the data of year we have to use.
Yeah, 3 year worth of data.
Oh, 3 years worth. Oh, okay.
Yeah, still use 3 year worth of data. Yeah, so you use 3 year worth of data, you calculate the mu. The mu will be in month, right?
Yeah. So the time directly time 12 or
I think you just times 12. Yeah, that's right.
oh,
I don't think there's anything fancier than that, right? Yeah.
because I just in the past I just put out every day of the end of the year and from the history from the maybe 2002.
When you go all the way back, you mean?
Yeah, this is my first time, but
Oh, that's fine. I mean, again, right? That's the whole point of playing around with this data to learn, right? But the whole point of dealing with historical data is I feel like if you go back very long, it may not make much sense.
yeah.
I would say that also makes sense, right? So it's good to check the two to see what wait, hold on. Ife, like when you do that, right, you got to be careful because that formula, let me see here. The R there, right, is not the mu. You know what I'm trying to say? The R there is mu dt, I think. So you got to be careful, right? R there is not mu. R is mu dt. Yes. So that formula seems also to make sense, but there's a tricky concept here, right? Mu is not the return, but mu is the rate of return. Mu should be calibrated by dt. Does that make sense? So I'm asking for mu annual, right? I'm not asking for return rate annual. So wait, hold on. God damn it. Sorry, I'm confused here. One second. Yes. So here's the thing, right? Yeah. So Ife, what you're writing is about return formula, right? On the other hand, here in our model, right, mu is a rate of return. So when you use monthly data, that means that your dt is 1/12 of a year. So in fact, right, you should, you know what I mean? So you take the expectation on the left hand side, multiply by 12, then you got mu using the mathematical formula in 2C, right? What you're saying is about the relation between return and annual return, monthly return and annual return, which is also correct. But we're asking for return rate. So I think there's a subtle difference between what you say and what the 2C is. You should get the same answer, but right now I cannot think of the direct answer to your question. But right, I mean, you just look at the formula I wrote. Expectation of R, right, is mu dt. Yes, expectation can be calculated by what? By average out your data, right? And so dt, right, is clearly, because you do monthly data, it's 1/12 year, right? So therefore, when they ask for mu, you just take the left-hand side, multiply by 12. Does that make sense? What you say is correct, but I think you have to be careful on how you extrapolate the mu out of that answer. I think you can compare your answer with Sinan and see if you guys get the same answer. I think you should, but you know, I'll be a little bit careful there. Does that make sense? Yeah, compare your answers. I mean, exchange notes, whatever. I think that would be good, right? I feel well. I did think of what you say too, but I think multiply by 12 is also one way, just from the formula. Yeah. Yeah, Sinan, what? Oh yeah, I was saying something like this, right? It's good to play around with data, but like when you deal with historical, right, data, one thing you learn is that different periods of history definitely has very different behaviors. So if you go very far back in time, actually your data doesn't make much sense because you're averaging out over different periods, different regimes, right? So it doesn't capture anything. So we go back 3 years, it's already kind of like you can question whether that makes sense. I just throw 3 years to, kind of get you guys to the work. But the last 3 years, right? Are we in the same regime, right? We had the pandemic, things may change, right? So anyway, I mean, that's the question. But I'm just saying, like in reality, if you want to work, then you want to be careful of how far you go back, right? And what kind of period you use, because it may not reflect the same kind of behavior, right?
Yes, this makes sense.
Mm-hmm.
Thank you.
Yeah.
Can I also ask one more question? The last question.
Sure.
Yeah. For the part for the one period binomial model is like we have to fix the step of the binomial model, right? Step like one period, just one steps. So
one period is one step, but also that means delta t, right? Is t.
yeah, delta t will be in fact like this one, right? If we fix the step and the t is the expiry.
So I think it's the other way, right? I mean, I think that you should fix n, right? Because
yeah, fix n
and then do the dt to be t over n, right?
Yeah.
Rather than here you fix you choose a dt first and then you find the n, right? But I mean, it doesn't matter because here we want the periods rather than dt. But it's the same idea actually, because the point, right, is if you use the binomial model with dt becoming smaller and smaller, right? Actually, that's how I code it, right? Then but there's you can do number 4 with dt getting smaller. I don't mind that. Yeah, I just say that the spirit of question B was it wants number of periods, so you can fix that too. But yeah.
Okay, thank you, Professor.
Mm-hmm. All right, any other questions? Okay, then if not, then I'll see you in class next Monday. All right. Yeah, thanks. All good there, Fatima?